Seaborn, as we all know, is a data visualization library available in Python. It's based on Matplotlib and allows creation of statistical graphics. It also has a number of functionalities such as an API that is based on datasets allowing comparison between multiple variables. It also supports multi-plot grids that in turn ease building complex visualizations. It has univariate as well as bivariate visualizations available to compare between subsets of data. The availability of different color palettes to reveal various kinds of patterns. It also estimates and plots linear regression automatically. So now, if you were wondering why use Seaborn when you already have Matplotlib, here is the answer to it. Michael Wascom, who's the creator of Seaborn, says, if Matplotlib tries to make easy things easy and hard things possible, Seaborn tries to make a well-defined set of hard things easy too. Factually, Matplotlib is good, but Seaborn is better. There are basically two shortcomings of Matplotlib that Seaborn fixes. Matplotlib can be personalized, but it's difficult to figure out what settings are required to make plots more attractive. On the other hand, Seaborn comes with numerous customized themes and high-level interfaces to solve this issue. When working with pandas, Matplotlib doesn't serve well when it comes to dealing with data frames, while Seaborn functions actually work on data frames. Now that you have an idea about Seaborn, let's move on to see how you can actually install this library. To install Seaborn, you can use the simple pip install Seaborn command, or if you are using an Anaconda platform, you can just go to the Anaconda prompt and type conda install Seaborn. Since I already have it installed over here, I'm not going to redo it again. Now let's get back to our presentation and take a look at the dependencies of Seaborn. Seaborn basically has 4 mandatory dependencies, which is NumPy, SciPy, Matplotlib, and the pandas library. It also has a recommended dependency, which is the stats models library of Python. So just like we've installed Seaborn, we'll have to install NumPy, SciPy, Matplotlib, and the pandas library. To install these libraries, you can use the same commands which I showed earlier with the name of that particular library. Okay, so I hope everyone's clear till here. So now let's move on and take a look at the various plotting functions in Seaborn. Seaborn has a number of functions that are available for visualizing statistical relationships, plotting with categorical data, visualizing the distribution of a dataset. Let's begin with visualizing statistical relationships. The process of understanding relationships between variables of a dataset and how these relationships in turn depend on other variables is known as statistical analysis. In today's session, I'll be using the relplot function to plot various statistical relationships. Relplot is a figure-level function that makes use of 2 other access functions for visualizing statistical relationships. These access-level functions are scatterplot and lineplot, which can be specified using the kind parameter of the relplot. To explain this in detail, let me jump onto my Jupyter notebook from here. I'll just open a new Python notebook. I hope everyone's familiar with Jupyter. Okay, I'll just rename this to Python Seaborn tutorial. Or I'll just say Python Seaborn and I'll rename this. Before we begin data visualization with Seaborn, we'll have to import Seaborn along with its dependencies. So the first thing I'm going to import is NumPy. Import NumPy as NP. Then I'll import pandas as PD. Import matplotlib.pyplot as PLT. And then I'll import Seaborn. Import Seaborn. Sorry for the spelling mistake, guys. This is import Seaborn. Import Seaborn as SNS. And I'll just execute this. Like I've already told you all before, you can load any dataset present on the GitHub and make use of it with Seaborn. Seaborn also allows you to load any dataset from Git using the load dataset function. So let me just load the flights dataset. So I'll just say sns.load_dataset. And I'll specify the name, which is flights. Okay, so now let me just go to the GitHub website. and open the flights dataset over here. As you can see, there are a number of datasets that are available which you can use along with Seaborn. So let me just open the flights dataset and scroll down. So as you can see over here, there are 3 columns for the year, month, and the number of passengers. So I'll just come back to my Jupyter notebook and I'll use sns.relplot. And I'll specify what I want my x-axis to be. So I'll just give x-axis as the number of passengers. And to the y-axis, I'll give month as the parameter. And for the data, I'll use A, which is the variable wherein I'm loading the data set. And I'll execute this. Okay, so I hope you're clear with this. So as you can see over here, the y-axis has month and the x-axis has the number of passengers. These points are plotted in 2 dimensions. To add another dimension, you can add the hue semantic. So I'll just copy this, Ctrl+C, and I'll paste it over here. And I'll give another parameter over here, which is hue, and I'll say that is year to be the hue semantic, and I'll hit run. So I hope you see the difference over here. The year has been marked as the hue semantic, month, which is in the y-axis, and the number of passengers, which is on the x-axis. So as you can see on the screen, this is nothing but the scatter plot. So in case you want a line plot, all you have to do is specify the kind parameter of rel plot with the keyword line. So let me just load another data set over here. So I'll say b is equal to sns.load underscore dataset, and I'll load the tips dataset this time. After this, I'll use sns.relplot. I'll specify the x-axis to be the time and y-axis to be the tip. Data is nothing but B and kind is line. Now let me hit run. Okay, so I hope you're clear with this. Now let's get back to our presentation and see how you can plot categorical data in Seaborn. This approach basically comes into picture when our main variable is divided into discrete groups. To achieve this, we'll be using the catplot function available in Seaborn. Like relplot, catplot is also a figure-level function characterized by 3 families of axis-level functions, which are scatterplots, distribution plots, or estimate plots. Okay, now let me jump onto my Jupyter notebook and show you all a few examples regarding this. Okay, so here I'll use the same tips dataset, and since I've already stored it in the variable b, I'll just use sns.catplot, and I'll specify the x-axis to be the day, y-axis as the total bill, and data is b. Now let me hit run. Okay, as you can see over here, this is the scatterplot that we've got using the catplot function. Scatterplot is basically the default type of catplot. However, you can change the kind of plot you want by specifying the kind parameter like we've done previously. You can choose between any options, which is strip plot, swarm plot, box plot, violin plot, etc. Let me just show you what happens when I change the kind parameter of this catplot. So I'll just copy this and I'll paste it over here, and I'll specify kind to be as violin plot. So I'll specify the keyword violin and I'll hit run. Okay, so I hope you see the difference. This is our scatter plot and this is our violin plot. So if I change the kind parameter, our plot will change correspondingly. Let me just give the type as boxin now. Okay, so I hope you're seeing the difference, guys. So now let's get back to our presentation and see how to visualize the distribution of a dataset. Visualizing dataset basically deals with understanding datasets with context to being univariate or bivariate. Okay, so now let's get back to our Jupyter notebook and see how you can actually plot univariate and bivariate distributions. So before doing this, I'll just import stats from the SciPy library. So from SciPy, import stats. And I'll hit run. Okay, so first let us plot univariate distributions. To plot univariate distributions, you can use the distplot function. So let me just take an example. C is equal to np dot random. I'll just use random.normal functions to draw random samples from a normal distribution. So I'll just give the corresponding parameters to it. You can give any parameters of your choice. I'll say size equal to 100 and scale. I'll specify the scale to be as 2 and I'll hit run. I did not specify the distplot function, so I'll use sns.distplot and I'll pass the data to it as C. Okay, so this is how the distplot function works. So this is an example of a univariate distribution. So now let's move on and see how a bivariate graph is going to look. To plot bivariate distributions, you can make use of the joint plot function. I already have a small example typed over here, so I'll just copy paste that and I'll show you all how it actually looks. Okay, so this is basically a bivariate distribution. So I hope you see the difference. This was our univariate distribution and this is our bivariate distribution. Moving on, Python Seaborn also allows you to plot multiple grids side by side. These are basically plots or graphs that are plotted using the same scale and access to aid comparison between them. This in turn helps the programmer to differentiate between the plots and obtain large amounts of information. To plot multiple graphs, you can either use the facet grid function or the pair grid function of Seaborn. Let me jump onto my Jupyter notebook and show you all an example of each of these. So first I'll be using the facet plot function. Okay, so here I'll load another data set. So I'll just say A is equal to sns dot load dataset. And this time I'll load the iris dataset. And I'll say B is equal to sns dot facet grid, which is the name of our function. And I'll specify A wherein our data is present. And I'll specify the column to be the species. I'll specify the column as the species of flowers. And then I'll just use the map function. And I'll specify all of them to be as histograms. And I'll give the parameter as sepal length. Now let me hit run. Oh, sorry, I made a spelling mistake over here. It's capital F. Okay. So I hope you're clear with this. I basically have 3 graphs that are available for the 3 species of flowers, which is Setosa, versicolor and virginica. As you all can see, it becomes very easy to differentiate between them. You can also make use of the pair grid function when you have a pair of variables to compare. Let me show you a small example of that as well. So here, I'll just say A is equal to load underscore dataset. And I'll load the flights dataset. And then I'll specify B as sns dot pair grid, and I'll specify the data to this as A, and I'll use the map function again to plot them. This time I'll use a scatter plot, so plt.scatter. Sorry guys, I forgot to specify sns over here, sns dot load underscore dataset. Okay, so I hope you're clear with this. So as you can see, the output clearly compares between the year and the number of passengers in different ways. Seaborn also allows you to make your plots more attractive and delightful. So till now, as you've been seeing, I've just had a white background for all my plots. So in case I want to change this, or if I want to change the color palettes that are available in my graph, I can do so easily. Let me just jump onto my Jupyter notebook to show you all how to do this. So here, I'll just copy paste the previous example. I'll just copy this and I'll paste it over here. And to this, I'll just use another function, which is the set function, and I'll specify the style of my plot to be dark grid. And I'll hit run. I hope you see the difference between the two. Here I have a white background, whereas when I specify dark grid, I have a different background with dark grids that are seen clearly. You can change the style parameter to any of the available themes, which is dark grid, dark, white, etc. So if I just specify dark and I hit run, you can see that the grids have vanished, but the background is dark. Not just this, guys, you can make many other changes to your graphs, such as adding or removing axes, the colors that are available, etc. Now let me just show you all how you can remove the axis lines that are present in your graphs. I'll take another example over here. So sns.set. I'll set the background this time as white. I'll say style equal to white. And I'll specify the color code parameter to be true. I'll load the tips dataset again. sns.load dataset. And I'll load the tips dataset. Then I'll use a box and plot. Or I've used the box and plot, so this time I'll use the box plot function. And I'll specify x-axis to be the days. And sorry, it's day, not days. And the y-axis to be the total bill. And data is nothing but A. Oh, sorry guys, I've made a spelling mistake over here. It's color codes. Okay. So here, as you can see, my plot has axes all around it. Now, if I want to remove any of these axes, all I can do is use the despine function. So I'll just copy paste this and I'll use the despine function. I'll specify the offset parameter to be 10 and I'll specify trim parameter as true and I'll hit run. Okay, so I hope you see the difference. So as you can see over here, I've specified the offset to be 10. I do not have the axes that are present before that. Seaborn also provides a number of color palettes, and to check the color palettes that are available in Seaborn, you can just use the color palette function. So I'll just use C is equal to SNS dot color palette. And this time I'll use the palplot function. And the data is C. Okay, so as you can see, these are the color palettes that are currently available in Seaborn. For deeper variations, you can use other functions such as the HLS palette, HUSL palette, etc.
So first of all, the question is, what exactly is data? So if you go by the definition, the data is nothing but, in general terms, refers to the fact and statistics collected together for reference or analysis. So those facts and statistics may vary as per the organization or as per the field that you're talking about. It may be data related to banking systems, financial systems. The data may be related to any of the other varied areas. That may be any kind of research related data. That can be any of the general data related to the population of a country, things like that. So it can be any facts. And when we take all those facts for any kind of reference or that's been shared for some kind of analysis in order to come up with some kind of a result, then we term that whole collection of facts as data. So if I'm talking about those facts and data, or those facts or figures or statistics, can I have different types of facts and different types of statistics? Let's see. So we broadly classify the data into two types. We call it as qualitative data and quantitative data. If you go by the meaning of this term, data, you will see qualitative tilted more towards where we don't have any of the numerical stuff, or we have the properties or the characteristic of the data available with us. That is characteristics or descriptors, those that cannot be easily measured, but can be observed subjectively, such as smell or taste or textures. So all of these kind of things comes under qualitative data. Second category is quantitative data, where, as the name suggests, we are talking about something measurable because we're talking about in terms of quantity. So quantitative data deals with numbers, things you can measure, dimensions such as height, width, length, temperature of room, temperature of a country, temperature of an area, humidity, like that. So further, if you go into detail of qualitative, you can broadly divide qualitative data into two types. One is called nominal data, another is called ordinal data. So if you talk about nominal data, so as the name suggests, It represents some kind of characteristic. Let's say if we're talking about gender of a population or of a race, then we can say that the gender can be of male or female. You can say name or characteristic that that data represents. It is sometimes called as categorical data as well, that has one or more categories, but there is no intrinsic ordering to the categories that you can see here. There is no ordering. It doesn't matter whether male comes before, females come after male or before male. It doesn't matter. The ordering here doesn't matter. So these kinds of data is called as nominal data. So if you try to understand this, the same example with the help of R, you will see that it all depends on what kind of input is entered by the user. Let's say, for example, it's being prompted to enter input number one. So that is being assigned to answer number one. And again, the input is being assigned to answer two. We have taken two variables and we are just putting a check. If you have placed as yes to the answers, then we can simply say print a message that welcome to the girls club. Other than that, then you just print a message saying sorry boys, you cannot join the club. So all of these results or the print statements are executed on the basis of the answer given by you, which is nothing but kind of a simple mentioning of any of the characteristic, or you can say just answers entered by the user. It's very trivial example to represent that what exactly is nominal data. When you say ordinal data, that means there is some kind of inherent order associated with that kind of data. So there is an ordering of the variables. Now, if you see this example here, we're talking about the customer IDs and a rating associated with those customers. So let's say we have customer ID number one, which is having ID of 101, and the rating given to that particular customer is strongly agree. Similarly, 302 disagree, and similarly the other neutral agree and strongly disagree. So if you see, there is an inherent ordering is already in place there, and that ordering is starting with a very strongly agree, which is customer ID 101, till it goes to the another customer with the rating scale of strongly disagree. So there is an order because strongly disagree one will be pretty much in low priority compared to the strongly agree one, or the neutral one will be somewhere in the middle. So the value which is associated with particular variable or with particular data having an inherent order is called as ordinal data. So if you want to take the example of ordinal data, it's pretty simple and straightforward. Here, if you talk about the marks, so the value of the marks has some inherent order, because the check that we have placed here is the value of the marks is less than 40, then that student is considered as fail. If it is between 40 and 50, then it's a second class. If it's between 50 and 60, that's a first class. And if it's more than 60 or equal to 60, then message is congratulations, you got a distinction. That means the value of marks has an inherent order, because if it is less than 40, then it has some different value and it has some different consequences. If it has something else between 40 and 50, it has something else, and respectively for other values it has some other significance. So because of the order present with the data, we call that particular kind of data as ordinal data. Let's go back to quantitative data now. So as I already told you, quantitative data is nothing but the data that we can measure, or the data that has some kind of quantity associated with that data. So the data that deals with numbers are broadly classified into quantitative data, and they further can be classified into two types. One is called as discrete data and the continuous data. When I say discrete data, that means the data that you can count, that has a specific defined value of it, that involves in integers. For example, we just saw about the mask. So how much marks you got is the discrete data. How many runs scored by a batsman is a discrete quantity that we can measure. Take a look at this example. We're talking about the data related to the mobile phone companies, and the mobile phone company is being represented by the column called organization, having Samsung, Apple, Nokia, LG, and Sony. And the number of the product given by those organization is being presented in the column called number of products. So if you see, Samsung has a definite or discrete value of 500. Apple has a definite and discrete value of 30. So these kinds of data is called as discrete data, because we have finite number of values possible with that particular data, or we can say product. You cannot further subdivide it. You cannot further change the units or something else, because that's a discrete quantity we are talking about. Unlike the same thing, when we talk about continuous data, that is also includes measurement, but that can be further divided, or you can say that can be further finer increments and modifications, or you can say further levels. Let's see here. If we're talking about the patient and the weight of the patient, then the weight of the patient is represented in the form of 86.5 kg. But the same weight can be represented in pounds as well. That can be further represented in the quantities of the grams and to whatever level. So we can further modify or reduce to any level we want. That kind of data is called as continuous data, which can be measured on a continuum or a scale. So why I'm telling you all this? Because based on these categories, whether you're talking about the discrete or the continuous, later on you will see we have a different distributions related to these kinds of data sets. When you talk about discrete data, you will later on see a binomial distribution is coming into the picture. Poisson's distribution is coming into the picture based on different representations of that data. Later on with the continuous data, you will see probability density function is coming into the picture. So different kinds of data normal distributions come into the picture. Different kinds of data projections, or you can say distributions, arise from these kinds of data. It's important to at least understand the meaning behind all these kinds of different jargons. So apart from the data, now we are talking about variables. And we all know in the mathematics, we have an habit of taking variables, right? If you wanted to solve any of the equation, let's say y equals to mx plus c, then you have y and x as two variables. So it is nothing but it represents an unknown value or a value that varies. That's called as variable. The variable can be further divided into so many categories. It's like categorical variable, control variable, independent variable, confounding variable, and dependent variable. So when we talk about categorical variable, that means it fits into some kind of a category and does not have a numerical value associated with it. It is unlike a normal variable that we normally see in mathematics, right? Because mathematics, we normally define a variable, say, for example, x, and we assign a numerical value for it. But unlike that, we have a different categorical variable that holds a kind of a non-numerical value. And let's say when we are talking about the categorical variable, that value can be of English type, or let's say if we're talking about values associated with the college subjects, then we can store those values in variables, values like English, mathematics, and political science. That value is stored in a variable, and that variable is called as categorical variable. Then after that, we have another variable called control variable. A control variable is a variable which is meant to be kept constant. Now, why it is meant to be kept constant? Let's say, for example, if you're talking about growth of the plants in a simulator, we can say controlled environment, because most of the experiments or the research, they're all being done in a controlled or a regulated environment. Now, why we need to do that is because whatever the figures or whatever the research analysis that will be proposed at the end shouldn't be varied based on some external effects or external quantities. Right. So we need to make some of the things constant. Let's say, for example, if you are trying to measure the growth of the plants in a simulated environment, so let's say you can keep the amount of sunlight as a constant variable, or you can say control variable. Because if you keep on varying the sunlight, then what kind of analysis, whatever analysis that you're doing on your plants, that may has some of the varied effects. Right? And those variables are called as control variables. Then you have independent variables, variables which is changed by the researchers or the person who is doing all that research or analysis, called as independent variable. For example, if you're investigating how changes in size of water faucet, of amount of water flow, the faucet size is your independent variable, and you have no control over the amount of water which is flowing. Or let's say, for example, if you're trying to measure, let's say a very simple example, if you're trying to measure the length of a wave versus the time in a day. So the time in a day is your independent variable because you have no control over that, right? But that time has very significant effect on the output of your whole analysis of getting the relationship between the time and the height of the waves. So the height of the waves is your dependent variable, and the time that we are talking about is your independent variable. That is how we further classify into two categories, independent and dependent. Then we have one more quantity, or you can say one more type of variable called confounding variable. In order to understand confounding variable, let's take an example. Let's say we have 200 volunteers. Out of those 200 volunteers, we have 100 as men and 100 as women. That the lack of exercise basically leads to weight gain. But we are only considering one variable here, lack of exercise. What about how much you eat? We are not taking into consideration that. Or when you're talking about volunteers, we have 100 women and 100 men. There's one more saying that men can eat more than women. We are not taking into consideration that fact, or you can say that point. So nothing was mentioned about starting weight. Nothing was mentioned about the occupation. Nothing was mentioned about the age. So these are called as your confounding variables. Because here men can eat more than a woman. So his sex can be a confounding variable again. And we are not taking into consideration all the other factors that may lead to significant changes in the output of your whole exercise or analysis. So those kinds of variables are called as confounding variables. Let's take a look at a simple experimental research example. Now here, in this experimental research, the aim is to manipulate an independent variable and then examine the effect that this change has on dependent variables. Let's say there are 100 students completing a math exam where the dependent variable was the exam marks and the independent variable were revision time and intelligence. Now, if you try to relate the revision time and IQ with the exam score, you will see a linear relationship between these two variables. That means the more the revision time, the better the exam score. The less the revision time, the less the exam score. So what they have done, they have divided the group. There are 100 students and the group is divided into two. One is having 50, another is having 50 students. And the instructions given to the group number one is that they have to revise for 20 hours and the group two students shouldn't be allowed to do any revision. And then if you try to compare the results of these two, since we already know there is a linear relationship, then you will see how if you're varying this quantity, the result is getting affected. Giving you a result of analysis that how the dependent and independent variables changes the whole scenario. Another example is non-experimental research. In non-experimental, the researcher does not manipulate the independent variable. We're not changing the independent variable. This is not to say that it is impossible, but it will be impractical. Let's say the researcher who is interested in the effect of the illegal recreational drug use, which is the independent variable for your information in this case, on certain types of behavior. That means what is our objective, the dependent variable that is going to affect it with the inclusion or exclusion of the independent variable. It will be unethical to ask individuals to take illegal drugs in order to study what effect this had on certain behaviors. So this is kind of a non-experimental research. If you cannot modify the independent variable that has its own effect on dependent variable. Now let's talk about the more technical sense of or technical jargons. And mostly we'll be talking about population and sample. So what exactly is population? So whenever you start with any kind of data analysis or any kind of analysis that you have to do on some kind of input sets, then whenever you get the whole data set for which you have to provide your analysis, let's say we are giving with the, say for example, last 10 years weather information of a particular region. And those last 10 years data can be huge data. So whatever input data given to us, and we need to come up with some kind of analysis, that whole data set is called as population. So normally speaking, you normally won't go and apply the whole analysis or whole mathematics on the whole population. The idea is to come up with some kind of a sample out of that population. So let's say if you have 10 million data set values, and in order to take sample out of it, you will start with 10,000 or maybe 1,000. But there is again a science behind how to get that 1,000 results or how to get 1,000 results from the 10,000 data set points that we call as sampling technique. So sample is nothing but some of the randomly chosen points or you can say data sets from the whole population set. So the idea here is take the sample out of whole population, put your analysis on that sample, come up with the analysis results and try to represent that analysis result on the whole population set. That is the whole idea behind sampling and population. So how to get that particular sample, because that sample shouldn't be biased, shouldn't be blindly chosen sample, because that blindly chosen sample may have some of the bias related terms which may affect the results, right? So we need to choose the sample pretty logically. So that is why we have sampling technique. So there are two types of sampling techniques available. One is called probability sampling, another is non-probability sampling. In probability sampling, it is basically based on the fact that each member of the population has a known or equal chances of being selected. When I'm saying selected, that means for becoming a part of the sample. So for example, if you had a population of 100 people, each people would have odds of 1 out of 100 of being chosen. So if you have to choose out of 100 people, so each and every individual has an equal and likely chances of getting chosen. That is what we call as probability sampling. Another is non-probability sampling. With the non-probability sampling, those odds are not equal. For example, a person might have a better chance of being chosen if they live close to a researcher or have access to a computer. So there are some unforeseen circumstances that may actually affect the sampling of the data. Because I told you, if you want to choose a person out of 100 samples, so you might choose your neighbor before the other samples or the other people because of the closeness and other factors. That is called as non-sampling or non-probability sampling. Probability sampling can be further divided into three types. We call it as random sampling, systematic sampling, and stratified sampling. Random sampling is very basic sampling technique. In this one, we select a group of subjects for study from a very large group. And each individual is chosen entirely by chance, and each member of the population has an equal and likely chances of being included in the sample. That's what is a very basic sampling is in this as a first representation of your probability sampling, and we call it as random sampling. Another sampling is stratified sampling. In the stratified sampling, there may be some factors which divides the population into some population, like some kind of a groups or a stratum. The measurement of interest may vary among the different subpopulations. A stratified sample is obtained by taking samples from each stratum or subgroup of the population. The proportion of each stratum in the sample should be same as in the population. That's what the logic behind. And it is being very frequently used when you have a population of heterogeneous records. When I say heterogeneous, that means mixed records are there. And we can let's see in this slide where we have divided the whole population into male subset and the female subset. So we subdivided into category based on subset. And then further, we can start with our random sampling again, the same part of stratified sampling as well. Systematic sampling is very, very simple sampling. In this one, what we'll do, we'll start with some kind of a repetitive technique. Say for example, we always start with taking into consideration every fourth record or every second record, right? So it's pretty simple. It's kind of a, you can say, ordered sampling we are doing here. That's why the name it is as systematic, because we have a particular system for that. So we need to take every second or fourth or sixth, whatever the record you have to take, and you have to keep on repeating the step again and again. That's called as systematic sampling. Now let's come back to non-probability sampling. So non-probability sampling, you can say it's not a product of randomized selection process. There's no randomized selection process included here. Here, the subjects are selected on the basis of their accessibility or by the purposive personal judgment of the researcher. Some of the external factor, there's no mathematics there. So basically, these kinds of sampling, we have a problem of sample representing the entire population is not confirmed. So therefore, they cannot be used in generalization of the entire population. So these kinds of techniques not that frequently used in order to generalize for the whole population. We can further divide non-probability sampling into 4 or 5 types. Sometimes you will see 4 different variations and sometimes you see 5. So we broadly classify into convenience type, consecutive type, quota type, judgmental, and snowball. So what exactly is convenience non-probability sampling? So as the name suggests, the samples are taken based on the convenience of the researcher or the person who is doing that analysis. That is called as convenience sampling. Then we might have consecutive as well. So whatever the samples that you have available as a part of that particular process, you will include all those samples. We call it as consecutive. Then we have quota. In this one, we need to actually, the researcher ensures that equal or proportionate representation of the subjects, depending on which trait is considered as basis of the quota. Let's say if you're talking about college students, so the college year level can be considered as your quota, so that we can divide into first year, second year, third year, fourth year, things like that. That is called as quota sampling. Then we have judgmental sampling. In judgmental, the researcher should be having a specific purpose in mind, where based on that specific purpose, some of them may be more deserving than the others, based on, let's say, what are the samples we are taking. If we're talking about English speaking people, so the people who are native English speakers might be given favor compared to the other. Like so based on the judgment of the researcher or the analyst, you can include some of the samples. Then we have snowball. In this type of sampling, the researcher asks the initial subject to identify another potential subject who also meets the criteria. So that is called as snowball sampling.